Dr. Alberto Cellino. He's a true Torino. Am I correct? You know, he was born in Torino, yes. And stay in Torino and work at the Torino Observatory. He's very well known, extremely well known in the asteroidal field, and have contributed greatly to enrich the field. But he today, you know, he's going to tell us about his work on Gaia, about the data analysis of the asteroidal data of the Gaia mission. And I think that's a very interesting thing. And he's, as far as I can tell, he's responsible for the Gaia asteroid data archiving and processing and also analysis. So I really look forward to this talk. We have been waiting for this talk for almost 10 years now, Alberto. So please go ahead.
Thank you. First of all, I'd like to thank you and all the organizers for inviting me to give this lecture. The real topic is how Gaia is in synergy with ground-based and activities. How it is time now to, in my opinion, to try and face the new situation due to the Gaia data in order to complement them with all we can do from the ground and in laboratories and so on. This is the main subject of my talk today. So just to a very short introduction of the subject for those who are not possibly familiar with small bodies of the solar system, and in particular the asteroids. Of course, there are two main reasons we want to study them. One is the purely scientific interest, because they can give us a lot of information about the story of the solar system. And then there is also the problem of the hazard represented by the existence of asteroids that can intersect sooner or later the orbit of the Earth with some well-known possible consequences. So what would you like to understand about asteroids? The short answer is everything. So we want to know how many, their inventory size distribution, their composition, their internal structures, the stories, and everything we can derive from our data, including also what can be useful to know about the possibility to develop credible strategies of defense from impacts in case this becomes necessary. So now we are now living a new era in Gaia, in asteroid science, due to the performances of this Gaia mission, who is collecting a lot of data in the field of astrometry mainly, but also photometry, spectroscopy. And these data are very important, and it is our duty to exploit them properly, trying also to make some fruitful synergy with what we can do from the ground to complement what Gaia is doing. And from the ground means applying some techniques that are not present aboard of Gaia, like polarimetry, and also in some cases making laboratory experiments that can be useful to better interpret the data that we can obtain from remote observations. So just to start this, I remember that a classical result of reflectance spectroscopy that we have been done from the ground since many decades is the discovery that, of course, the asteroids are not all the same. The reflectance spectroscopy of the objects are very heterogeneous, and you can use them to define a taxonomic classification like the one that you can see here in this small plot that shows the taxonomic classes defined by DeMeo and colleagues using both visible spectroscopy and also near-infrared spectroscopic data. Also, this shows another way to look at the data. These are the colors of the slow and digital sky survey. You see that in these plots, the objects are plotted with different colors corresponding to different main complex taxonomic complexes that can be identified by looking at spectrophotometric data. You see the big C complex, the S, the V, and then you can plot the asteroid main belt. This is a sinus of inclination versus the semi-major axis, orbital semi-major axis, and you see some apparent effects. On one hand, you can see that there is a general gradient of composition in the sense that you can see that the blue objects that belonging to the C complex tend to become much more abundant at larger heliocentric distances, whereas the S complex is much more common at smaller heliocentric distances. There is a general gradient, but if you look, it is clear that there is a lot of mixing that is also going on. We have not a belt with a sharply divided zone dominated by different taxonomic classes, but there are zones in which in every zone there is some mixing, and this can be very interesting from the point of view of what we can think about the origin and evolution of the early solar system. And then there are also these groups that you see in the plot in the right, these clumps, this cluster of objects that are the so-called dynamical families. These are swarms of fragments from the disruption of single parent bodies. And you can see that they tend to be very homogeneous. This is also important because this tells us that the original parent bodies were not differentiated as one could hope, but all the evidence is that they were homogeneous in composition. Coming back to the subject of the gradient and the mixing, this can be interpreted in a very general way by the current models of the early planetary evolution, the early evolution of our planetary system. In particular, if you there is the so-called Grand Tech model that explains many things, assuming that at the beginning of the history of the solar system, there was a very important migration of the newly born Jupiter and Saturn, and also later Uranus and Neptune. In particular, Jupiter and Saturn started to migrate inward, and then at some point this inward migration stopped, and that was what is called the Grand Tech, what gives the name of Grand Tech to the model. Jupiter and Saturn reached a status of mutual resonance and started to migrate outward. And as you can well understand, imagine, all this movement of these big objects in different ranges of heliocentric distances was able to strongly perturb the planetesimals that were forming in different heliocentric distances. and this produced a lot of mass removal because many objects were ejected from the solar system or moved to different position in the different heliocentric distances, and this eventually at the end of the process we obtained the current situation in which if you look the main belt asteroid includes objects having different origins, and so mixing as we can see in the data, in the spectroscopic data. This is important also because if we the last phases of this story of migration, of course, produced a lot of perturbations on the planetesimals, and there was a lot of bodies going forth and down, back and forth, and many collided with the newly born planets, and we know very well that all the surfaces of the planetary objects that we know are densely covered of craters, and this is also useful to understand if and when some objects had some geologic activity, because geologic activity is something that tend to delete, to remove the impact craters. So this is very, just to say very in general, what we are what we can already infer just looking at the distribution of the reflectance spectra in the asteroid belt. But now, as I was saying at the beginning, we are living in the new Gaia revolution era, and this means that we will have at the end of the mission the orbits with unprecedented accuracy, and then, but not only this, but also spin properties, reflectance spectra for a number of the order of 100,000 objects. This is a very big step forward in our understanding and knowledge of the asteroid belt, and the fact that Gaia will produce data of very high accuracy, mainly in the field of astrometry, means that we will have the possibility to determine the mass for the first time with relatively small error bars for at least 100 objects. And this is a very big improvement. Then you can add to this to the mass derived from mutual perturbations in case of close approaches between asteroids, and also from binaries that are ideal to derive the masses. If you couple this mass data with the size and shape which come from spin properties, from the photometry, as I will tell you later, then we can have the bulk density, mass, volume and mass, bulk density. And then if we couple the density with the taxonomy, we can for the first time make an interpretation of taxonomy in terms of composition and internal structure. And so this is a very, very important result. Gaia is preparing its own taxonomy based on reflectance spectra that for the first time after many years is including also the blue part of the reflectance spectrum that has been lost in recent years because the CCDs used in asteroid spectroscopy survey were not sufficiently sensible in the blue part. And the first release of Gaia reflectance spectra is imminent. This will be done probably in the month of June, the next June. So we are these data are just coming. And this first release will be an important one. It will include 50,000 asteroids for the first time. And then this is already an impressive description of what Gaia represents for asteroid science, but we should also think about the legacy of Gaia, and one of the big legacies will be the fact that the observations of star occultation by asteroids will probably become the most important and most accurate way to determine the asteroid sizes and shapes. This is inherent on what you observe when there is an occultation. You can derive, if you have different observers, you can derive different chords that of the object that is occulting the star. So you can not only derive an average size, but even a shape, a profile. And so far this has not been done from the ground, because that was the big problem, that to observe occultation you need to know with a very good accuracy two things. One is the location of the star in the sky, and it's very accurate sky coordinates. And the other thing is a very accurate determination of the asteroid orbit. So far, this has not been possible for the large majority of the object, because and all the possible occultation of stars that are not very bright, because the astrometric accuracy of their position in the sky were not sufficient. But now, after Gaia, this problem is going to be solved. So the future of occultations is very bright. You can take into account that currently, from a given observatory, you can hope to observe a few star occultations per year. But after Gaia, with the release of the catalogs of the orbits and the star position, you will have the possibility to observe several occultations per night. So this is a change of paradigm. But so far I spoke about how great is Gaia, but there is also something that is missing in this Gaia revolution. And this is due mainly to the fact that Gaia, which is this black circle in this plot, will never observe. It has always the field of view of Gaia is always at a minimum angular distance of 45 degrees from the sun, for obvious reason, no? And but this means that Gaia will never observe at a small solar elongation, but also it doesn't observe at the solar opposition for the symmetry of the geometry of this configuration. And so this means that we observe only between 45 and 135 angles degrees of solar elongation, and this has some consequences. In particular, from Gaia, it is not easy to, or even impossible to directly observe the absolute magnitude of the object, which is the magnitude observed at zero phase angle, because at solar opposition, this is not a region of the sky where Gaia observes. And also there is the fact that there are not aboard instruments that can be very effective in determining the geometric albedo of the objects. Geometric. So how much reflectant is the surface of of an object that scatters the incoming sunlight. The albedo is something that depends obviously upon the surface texture and composition. So it is an important physical parameter. Also because as you can see here, there is an important relation relating the albedo, PV, the absolute magnitude H, and the size of the object, supposed to be spherical or an equivalent sphere. That if you know two of the parameters, you can derive the third using this important relation. But the problem is that Gaia per se does not derive directly neither H nor the albedo. And this is just to mention the fact that if you look at the variation of the magnitude of an object at different phase angle, there is there is this typical kind of a behavior. There is a linear increase of magnitude for increasing phase angle. Increasing magnitude means that the objects tend to become fainter when they are observed at high phase angles. But close to the solar opposition, there is a nonlinear increase of brightness. And this is a problem because from Gaia, we can observe asteroids typically between 10 and 30. So in the linear part of this plot. But we cannot determine H, the absolute magnitude at zero phase angle because we have no data to cover this so-called opposition effect, which is not linear and non-predictable. This is a very old problem in asteroid science. This is the phase angle. I was speaking about that. The phase angle is nothing but the angle between the direction to the observer and to the sun as seen from the object. So zero phase angle means that the object is in a position. The apparent brightness of an object, of course, depends on the illumination conditions of the epoch of observation, the phase angle, as you can easily understand. In addition, it depends upon two fundamental physical parameters, which are the size and the albedo. This means that if you measure the brightness of an asteroid at a given epoch, and you do not know the size and the albedo, you cannot, you have an ambiguity. This can be a large dark object, or it can be a small brighter one, and this is the problem why you cannot use observation invisible to determine these two parameters. Also because the albedo varies by a factor of 10. So it is clear that the larger the objects in general and the brighter it will be. But the ambiguity between these two situations is still valid. And how to overcome this? The idea of the thermal radiometry is that if you observe an object not only at visible wavelengths, but also in the thermal infrared, then you have you obtain flux. You measure fluxes that one is a scattered sunlight, the other is a thermal emission due to the temperature of the object, and that both of them depend about both the size and the albedo. So if you measure both of them, you can solve the problem. This is in general terms. Take into account that the dependence of the thermal infrared flux is fairly weakly dependent on the albedo, but it is much strong. The dependence on the size is much stronger. And this is the situation. These are just to assess a little what can be the accuracy of thermal radiometry. You see, these are the sizes of objects determined using the thermal radiometry technique, using two data sources, two different satellites that have measured the thermal flux. And you see that the situation is fairly reasonable. There is good agreement. But if you look at the albedo, the situation is much worse. There are differences between the different computations that are huge, that correspond to objects having very different compositions and so on. And why this? This is also due to the fact that the thermal radiometry would require to measure at the same time the visible and the thermal infrared flux. But in practice, the wave magnitude measurements are never done simultaneously with the thermal infrared measurement. So they measure well the infrared flux, but then they do not have the visible, and they try to derive it from knowledge of the using this formula, in which you do not know PV, but you have the absolute magnitude from ground-based observations, and you have the size from the thermal infrared flux. But the result is that is the one that you see here, due to the fact that H is very poorly known in general. And so the question is, can we do better than this? And this is why we can start to think about polarimetry, because polarimetry is another observing technique which is important due to a number of reasons that are summarized here in this slide. Since I will touch all of these points in the following, I do not spend time here. But I will simply remind you what polarimetry observes. The idea is that the sun is a source of non-polarized light, but when the sun radiation is reflected, scattered by a solid surface, it becomes partly linearly polarized. This is again the usual definition of the phase angle. This is the PR, is the parameter which is usually used to describe the degree of linear polarization of objects of the solar system, where I perpendicular and I parallel describe the components of the polarized light beam scattered by the object, having the plane of polarization perpendicular to the scattering plane, the plane that includes the sun, the observer, and the object, or parallel. And according to its definition, this means you obtain this typical morphology of the phase polarization curves for asteroids, which are characterized by the presence of a so-called negative polarization branch, in which this PR parameter reaches negative values because E parallel is larger than E perpendicular, and this is something that is not predicted by elementary optics, like Fresnel laws or something like that. And then at a certain value of phase angle, which is normally around 20 degrees of phase, there is an inversion. The polarization, the PR parameter becomes positive and grows in fairly linear way until going to larger phase angles. Take into account that in this plot we are certainly looking at a near Earth object because the main belt asteroids cannot be observed at phase angle larger than something between 30 and 40 degrees. So all these right part is reachable only for objects that have a very close distances from the Earth, so the near Earth asteroids. Whereas in the case of the main belt, we only see this linear increase of polarization after the polarization inversion angle. And what does it mean, all this? The importance of this is that there are several empirical relations that have been found which link the albedo, the geometric albedo, and some of the parameters that describe this kind of morphology of the phase polarization curves. In particular, the slopes H, this slope of the linear part, the inversion angle, the extreme value of negative polarization, and so on. So the polarization, polarimetry is one of the best techniques to derive the albedo without knowing anything about the geometric, about the absolute magnitude and the size. And there are the best recipes, how to say, to derive the albedo from polarimetric parameters has been reviewed in recent years, and there are and you can see here a lot of numerical values for coefficients that describe the relation between some of these polarimetric parameters, including some that are not shown here, and the albedo. But I will not speak about this. Another interesting feature of polarization data is that if you plot the polarimetric inversion angle and the extreme value of the negative polarization, you obtain something like this. This is a classical plot that was produced by Dollfuss in the late 80s, and shows that you can compare. There are in these plots two domains which are corresponding to very thin dust of lunar origin brought back to Earth from space mission, from lunar missions, and these are bare rocks, and in between you see that you can find most of the asteroids of different taxonomic classes. These are the S class, this is the C class, there are the M something in between. This is a very old plot, but if you look at the more recent plots, the situation is still similar. Apart from the fact, if you look, there is some change on the scale. That now we know a number of objects that were not present here, that have very extreme values of the phase of the polarization inversion angle, both in one side and the other. But I will go back to this later. The first example of these strange objects with having a very high inversion angle is the case of 234 Barbara, which is first discovered in 2006 to have this kind of behavior, which were completely unknown and unique at that time. But then later some, you see, this is an object that have a polarization of 1%, negative polarization at phase angle, where most asteroids have the inversion angle. So it is, and after the discovery of Barbara, some other objects were found, which share the same behavior. An important thing is that they are rare. There are not many of them. There are only a few of them. And since a couple of years, a few years, we know that all the barbarians belong to one particular taxonomic class of the Meo. You remember the one that I was showing you just at the beginning. All of them are L taxonomy class for the male. The taxonomy classes are based on the reflectance spectra, and this means that this L taxonomic class is peculiar in many respects, and their spectra, some you can see some of them here, are characterized by a morphology which is interpreted in terms of high abundances of on the surfaces of these objects of the spinel mineral. The spinel is an interesting mineral because it is found. It is one of the components of the so-called calcium aluminium rich inclusions, the KAIs, that are found in many meteorites, and these are the oldest solid samples of solid material that we have found in the solar system. They are very primitive, and the fact that the barbarians are so have so large abundances of this particular mineral in their surfaces, it can be a clue that these objects are very, very old and most primitive. So this is important. This is the one reason why they are so important. Coming back to polarimetry, there is also the subject of the identification of possible main belt comets. So this means objects that have typical asteroidal orbits around the sun, but show episodes of typical cometary activity. These are objects that were not known until 10 years ago, something like that. But now there has been the discovery of several of them, and this means that also that the traditional difference that we have that has been accepted between the comets and the asteroids is not so sharp as we were used to know. But what is the importance of polarimetry in this story? The story is the following: in the 80s, when the taxonomy was based only on reflectance spectra taken at visible wavelengths, there was one class that was called F, which stands for flat, because these were objects that had very flat reflectance spectrum at all wavelengths down to the very blue region. And they were part of this BFG complex that were fairly rare and were known to exist. But with the development of CC detectors for astronomical studies, the blue part of the spectra, of the reflectance spectra of asteroids has been lost, as I was saying before. And this means that now, in modern times, the old F class has been merged together with the B class, for instance. However, if you look at the polarimetric properties of the objects that belong to the old F class, they display a very important property. They have a very short value of the polarimetric inversion angle. You see here the blue. We are not at 20, but a little more than 15. And another important fact is that some objects that were classified originally as members of the F class are known to have exhibited some evidence of cometary properties of emissions. So this is the case of Wilson Harrington, that was discovered as an asteroid, but then was also seen to have a cometary activity. Phaeton is the parent bodies of the Geminid meteorite. So there are good reasons to think that it could be a cometary body. And then also there are a few observational comets that were observed using large telescope when they were sufficiently distant to show directly the nucleus and without the coma. And in these cases, and at least in a couple of cases, they were also found to display a small phase polarization inversion angle. So these are two examples. This is the prototype of the B class, and this is the prototype of the old F class. You see that the inversion angle is different. But what is important is that recently, when there was the OSIRIS-REx space mission approaching Bennu, it had been found that Bennu was a member of the B class. But since the B class, the modern B class, includes also the old F class, we were wondering whether it could be, Bennu could be an F class, non-recognized in modern spectroscopy. And so we did a polarimetric campaign to observe it, and just to make a long story short, we found that it had a polarimetric behavior typical of the F class. And so we were saying in the paper that we published before the arrival of OSIRIS-REx, we published a paper on monthly notices saying that, okay, we have found that it is an F. This could be interesting because there are some main belt comets that are suspected to be F class. We do not state that F class equal comet, but at least in some cases this happens, and so it will be interesting to see what OSIRIS-REx will find. And OSIRIS-REx found hydrated minerals on the surface of Bennu and totally unexpected material spitting, so some kind of surface activity that was not expected at that time. So this was just to explain why polarimetry is very important and interesting, and this is one reason why there is a renewed interest about this technique, and in particular since a few years there is a new asteroid polarimetric survey that is carried out in Calerne, which is an observing station belonging to the Observatory of Nice in France, in which in this dome there is a 1 meter telescope equipped with a polarimeter built in Torino, my institute, and we are trying to observe as many objects as possible. Again, this is an important survey because it started in 2017, and we have already produced nearly 2,000 measurements, single measurements for a number of asteroids of the order of 500. And this could be compared with the 5,000 single measurements that are listed in the literature, but which includes observation carried out since the early 70s. So this means that we are very, very rapidly improving the data set of asteroid polarimetry data using CAPS. And for many asteroids, the CAPS observations are the most important or even unique source of information about their polarimetric behavior. You see in this and other plots, you will see that the red points are CAPS, Calerne data points, and the black ones are data from the literature. Of course, in CAPS, the barbarians are very important targets. and some interesting results have been observed in practice. Some difference in the depth of the negative polarization bands that could suggest, this is not sure for the moment, but might suggest that there are at least one subclass of barbarians. They are not all the same. And there is also, and this is also a matter for some laboratory activities that are in progress currently. And another important, interesting result obtained using CAPS data is that there are cases in which the data that suggested an object is a barbarian should be taken with some care, because if you, as usual, define as barbarian an object that has a fairly high linear polarization at a phase angle of 20 degrees, this is a classical way to say, oh, this is a barbarian. There can be cases in which you risk to draw incorrect conclusions, because this is an example of an object which is for 48 Doris, which is a CH class. This is a primitive object. It cannot have anything to do with barbarians. But if you look at 20 degrees and you compare with this, okay, it's not so different. Huh? There are missing data here. Maybe the situation, this fit is a little misleading. But looking just at the data, at the data points, they are not so important. And so this can be dangerous for those who discover barbarians by looking only at the polarization at 20 degrees. The fact that Doris has that polarimetric behavior does not imply that all the objects that belong to the same CH class do the same. You can see here many examples of these CH asteroids which have an inversion angle around 20 degrees. So nothing like Doris. We do not know why Doris behaves like this, but okay. And then speaking about polarimetry again, there are the near Earth objects that are important because they are so interesting for many reasons that we are already mentioned, and when we can observe them, we do. Now I have to run a little to the end of my talk, and I want to mention the fact that there is a research program going on that is related to Gaia, in the sense that there are 3 telescopes that are that have a program to observe, to measure the position of Gaia, the satellite itself, on the sky. One of these is the ESO VST telescope, and there are some others. This is needed because it is necessary to know with the maximum possible accuracy the position of Gaia in the sky, just to reduce the Gaia data. But what is interesting in this context is the fact that Gaia, since Gaia is in the Lagrangian L2 point, this means that when you observe Gaia, you are pointing your telescope to the region of the sky that is at solar opposition, in which the objects are in solar opposition, so 180 degrees from the sun. And this is interesting because in the plates taken by the ST and other telescopes, they discover a lot of asteroids that are not most of them are not known, are new detections, and are seen at solar opposition. And the numbers are important. Between 10 and 90 asteroids with a median of 35 per night. And so these are important in many respects, because on one side, if you have observations of known objects at the position, you can try and improve the wise albedo determination, because you will have a better estimation of the absolute magnitude, and you can use it as one of the parameters that enter into the computation of the albedo using thermal infrared albedo, as I was saying before. And then, but apart from WISE, there is also a fraction of the order of 1/3 of these asteroids detected by GBOT, which are objects that are sufficiently bright to be detected by Gaia also during the mission, the mission lifetime. And so this means that for these objects we can have some estimation of the magnitude at opposition, at zero phase angle, and this is important, and they can be also allowed to fit all the phase magnitude data, including Gaia and GBOT, in a common fits using for instance, the G1, G2 photometric system. Okay, and this is important. This is very final part of my talk, because in 2000, Beskay and Shevchenko found a relation between the slope of the linear part of the phase magnitude relation found by the objects and the albedo. And since, as you can see in this plot, and since this is the interval of the interval of phase angles in which Gaia collects its photometric data, this means that if such a relation holds, we can derive the albedo from photometric data of Gaia. This is the point. So it is very important to confirm that this relation exists and to obtain a better calibration of it. And so this is just an example of what I was saying from the beginning, how to have the possibility to complement Gaia data with very useful ground-based data coming from other sources. This is an example. If you have the photometric data by Gaia and also some estimate of the absolute magnitude from GBOT, you can have a determination of the absolute magnitude, H. On the other side, from the sizes that can have been determined from WISE thermal infrared data, and also from direct measurements of Gaia, because Gaia also will be able to directly measure some sizes of the objects that are largest. But you have sizes and the absolute magnitude, and so you can derive the albedo. And in this business, there is also polarimetry, which is important, because polarimetry independently can derive the albedos of objects based on their polarimetric parameters. And so all albedos determined by age and size can be checked or better constrained by using polarimetric data. And then when you have the albedo, you have the determination of albedo for a good sample of objects. You can look at the albedo slope of the phase magnitude relation determined using Gaia photometric data. And you can also look for differences in this relation as a function of different taxonomies, because objects having different surfaces can have different slopes, for instance, of the phase magnitude relation. And if you do this, you can have a confirmation and a better calibration of a relation between the albedo and the phase angle. And so this means when you look, you reach this point, you have just looking at the Gaia photometric data for tens of thousands of asteroids, you can derive from them, for them, the geometric albedo. So this will be another great result. So this is just to summarize the concept that merging data coming from different techniques, different sources with Gaia is very important, essential in this current situation, just for many important things, including the determination of albedos, the identification of asteroid dynamical families, and removal of family interlopers. I had no time to think about that. If you have some question, I will answer. To derive a new geologic map of the asteroid belt, to better understand the barbarians, other unusual classes of objects, and also to identify objects that exhibit comet-like properties. Sorry for having been a little late, but okay, this is the end of my talk. Thank you again for your attention, and I'm ready to answer for some questions if you have.
Okay, thank you so much, Alberto, for this talk on Gaia. A very extensive, talk.
Maybe even too much.
No, that's fine. And questions from the audience, and I want to ask a couple of people to say hello to you, because you have written to them, but they haven't seen their face. Sherry, can you turn on your camera and let the albedos see what you look like?
Should I interrupt the sharing of the screen or not? I don't know.
You can.
But I keep it in the case I have.
Yeah. Otherwise, he is Sherry. Who you have the correspondent with.
Yeah.
Hi, I'm Sherry.
Hello.
I was doing the polarization in Taiwan and used a tripod in Lulin Observatory. And recently, I have a proposal from your idea to looking for the variance.
Yeah.
It is still ongoing work.
You're working at Lulin Observatory, or not?
I used Lulin. 1 meter telescope.
Mm-hmm.
But the problem I can see is that your polarimetric observation using Cellino Observatory, you got very nice observation with a very small error bar.
But yes, the error bars have been increased recently because the problem with polarimetric studies is that to be able to accurately determine the role played by instrumental polarization, because you have to remove all components of polarization that are not due to the object that you are measuring, but to the optical system of your hardware, of your telescope and detector. And recently we found to do that, you have to observe routinely a lot of polarization standard stars for which you know that there is no polarization, or as opposite, they are very highly polarized. And if you do this, we have redone an assessment of all the zero polarization standard stars that we have observed in Calern since the beginning. And we have found that over short time scales, the instrumental polarization tends to be stable. When you make a given run of observation, you can be fairly confident that the polarization, the instrumental polarization, will remain constant for the duration of your run. But if you look over longer time scales, we have found that the instrumental polarization changes in a not predictable way, And so we have been led to add to our previous estimations of the error bars. We have been led to add quadratically a component due to the fact that over longer time scales the instrumental polarization is not so stable. So we had to add 0.8% of instrumental polarization to our error bars. Well, okay, they are still acceptable. 0.08%.
Yeah,
Sorry.
So as far as I can tell, doing polarimetric observations, the whole game is to deal with the error bar.
Mm-hmm.
And Sherry, sometimes she wanted to give up. So I always try to tell her that she's the second person in the world who's doing polarimetric observation of asteroids.
Yeah, we are not so many. Yeah, there is the Ukrainian team that now currently has, I think, other things to think about. Unfortunately.
So is Lu Xiaoping, James, are you there?
Yeah, I'm here. Okay.
Yeah.
Okay. Thank you, Professor Eve, for your sharing with us so important report from my old friend Alberto. Hi, Alberto. How are you? Well.
Sorry.
This is James.
Yes, James. Yeah. I'm very glad to hear you. Yes.
It's a long time not connect you. Because recently, I have spent almost 2 years on my new work in my faculty. But now I'm focused on some deep learning technology. And some applications, and recently I have a good news to share with you. Recently, I work with my PhD student Zhang Yuqun. Now he is also attend this online seminar, and we are build a new model for the binary asteroid under the state definition of the Cellino. So now we finished this signal, and in the near future, we expect that we can cooperate on the binary asteroid and some determinations for the parameters. I noticed that you mentioned that in the Gaia data, there are some observations for the binary asteroid. And by the way, in the data release 3 will be published in the university, the Gaia data release 3. Do you have some news?
The next Gaia data release that will be both somewhere in June will not include I think binary information, I think, but I know that during the validation, the data validation procedures that are done before the data release, there were some interesting cases of objects that displayed some wobbling. I mean, the position were oscillating, no, from left to right and right from left. Let me say in this way, as a probably due to the existence of a companion, and there are cases like this. And but for the moment, I think that this kind of very accurate astrometric data will not be explicitly included in the next data release, because these are very small and subtle effects that it is better to wait for the end of the mission, when there will be more data but in any case, yes, the identification of binaries is of course one of the most important goals of Gaia. These and the measurements of the deflection due to close encounters between asteroids, because these give you information about the mass of the large perturber.
So James, I suggest you go visit the Alberto in Torino.
This would be great.
Okay.
The problem is that I'm losing my office, because now I'm retired, but okay, they still allow me to come. So.
Yeah. Okay. So, thank you. In the original play, I would like you to visit us, but now it's a special case, and we have not go out for almost 2 years.
These have been very, very sad years, these ones.
Yes.
Before the pandemics and now the war, and the pandemics is still there, by the way.
Okay, there's another question. Lin Chi-Hong, you have a question?
Okay, so can you hear me okay, Professor?
Yes.
Okay, so good afternoon, Professor. So I have one question. Is we know something types the family. So they're inside the asteroid. Their qualities between the rock and the comet. So means this kind of asteroid sometime they will be released the gas. So it look like comet, but sometimes they did it. So my question is because we know something type this kind of asteroid that the Pizarro 7968. Pizarro, this kind of small asteroid, they'll be releasing a lot of gas from their surface. So is that possible that this kind of gas will be like the rocket jets and to change this the asteroid's orbit, so make the Earth scientists human will be hardest to predict their orbits? Is that possible?
Well, to be sincere, I'm not really an expert of these subtle effects of the change of possible changes of the orbit due to the gas release. I think that yes, some small effect should take place. It is not clear to me whether this can be seen by Gaia, for instance. I don't know, but maybe because Gaia is looking for, is characterized by an incredible astrometric accuracy, and they want to that should make it possible to measure very subtle effects, including, for instance, also the Yarkovsky acceleration, and these are very small effects, because so I cannot. It is possible, yes, that also orbital evolution due to the fact that objects have some degassing event could be detectable, and of course these objects do exist. We know that they are. There are many of them. Possibly they do not emit gas along all the orbit, but maybe only in some time, possibly at the perihelion, something like that. I'm not really an expert of this, but there are several of them, and well, I hope I have understood your question.
Yeah, I think Alberto, you answer him correctly. I mean, on one hand I think it's a very good and interesting question. Means that maybe the Gaia could be used to track the more active comets, right?
Yes.
Yeah, to look at the non-gravitational force. So that would be one. Okay, Lin Pyong, you should then study astronomy, right?
What?
Okay. Any other questions to Alberto? This is and Alberto already pointed out that there are already a couple of papers written. I mean, there's one in 2020, a year or two ago, and there might be even more recent one. So if you're interested in the Gaia results, then just go search for Cellino, and then 2020. I mean, something will come out, right?
Yeah.
Okay, good. If there are no other questions, I think we would end the lecture. Very interesting lecture right here. And I want to thank Alberto again, and I want to thank everybody for coming to this interesting lecture. And I will see you next time. I think that there we have another 10 or 20, lectures on asteroids and comets and small bodies lined up in the next few months. And
okay.
I welcome you to come. Yeah, thank you.
Thank you for having invited me. It was very great pleasure for me, and I have I'm very glad to have a good contact with your team, your students, and yourself, of course. Thank you very much.
Yeah, and now you have learned how to use Google Meet, right?
Yes, this is it's always time to learn something new.
Okay, great. Thank you.
Bye-bye.
Bye-bye.